Hi everyone. In this video, you are going to learn to write equations for rational functions. So by the end of this, you should be able to write a rational function given any critical values. So asymptotes, zeros, wholes, any of that good stuff. Okay, problem one says to write an equation for the rational function with this horizontal asymptote, so on and so forth. When you're approaching one of these problems, there's a lot of information. So I think the best thing you can do is take a look at one thing at a time. So I'm going to look at the horizontal asymptote and see how that affects the equation. Okay, then I'll look at vertical asymptotes. Then I'll think about zeros. And then I'll think about the whole. Maybe not in that order, but I'm going to think about each part separately. Okay, first thing that come to mind to me is I know vertical asymptotes are undefined values. Okay, you can write that down if you want. So with that said, these vertical asymptotes need to be in the denominator. I'm going to abbreviate that. Okay, where zeros come from when your y value is 0. And in order for the y value to be 0, okay, the whole fraction would need to equal 0, which means 0 needs to be in the numerator. So anyways, moral of the story is my zeros need to go in the numerator. So I'm going to start with that. So I have a rational function. I'm going to give my function a name. You can call it whatever you want. I often like smiley face of x, but in this case, I'm going to do star of x. So my function is called star. Okay, now I have vertical asymptotes at x equals 5 and x equals -1. So if x equals 5 is my asymptote, that means x minus 5 equals 0. So you subtract the 5 from both sides. Okay, and this is the factor that will go in the denominator. So I have x minus 5, and you can do the same thing for x equals -1. It'd be x plus 1. Okay, zeros work similarly, but they'll be in the numerator. So if I have a 0 at 1, 0, that means x is equal to 1, which means x minus 1 is my factor, my 0. So I'll have x minus 1. And then if it's -2, it'll be x plus 2. You could do the computation off the side if you need to. So I've got a pretty good start. I've got a numerator, denominator. I've taken care of this and this pretty quickly. Okay, the last things I need to put in are my horizontal asymptote, and I got to use my whole. Okay, first and foremost, horizontal asymptote. What does a horizontal asymptote do? Okay, now notice that, well, actually, let's do whole first. Okay, wholes are another example of an undefined value on the graph. So that means our whole needs to also be in the denominator. Okay, so I have a whole at x equals 4. Okay, so x minus 4 equals 0 is my factor. Okay, but wholes are a little bit different than vertical asymptotes. Wholes come from factors that cancel. So they're like in the simplified version, but they're not in the whole version. Okay, so this would be here originally, but then I would cancel this out, and that's what makes it a whole. Okay, so my whole comes at x equals 4. Okay, now I'm going to look at the horizontal asymptote. So notice that there are 3 x's here and 3 x's here. So if you distributed this all out, which I'm not going to do, you would have an x cubed in the numerator. If you distribute this all out, you would x cubed in the denominator. So since the degree in the numerator is the same as the degree in the denominator, the horizontal asymptote comes from the ratio of the lead coefficients. So with that said, the ratio of my x to the third up here and my x to the third down here, well, it says y equals 3, but it's really like 3 over 1. So the ratio of this should be 3x cubed over 1x cubed. So in order to make that happen, all you need to do is add a 3 over 1 here. Because if you FOIL this all out and get it in its standard form, you'd have x cubed, and then you'd multiply the x cubed by 3, which would give you the 3x cubed. And then this would all be multiplied by 1, so again, you still have 1x cubed. Do I really need to write that one? No, I don't. Okay, so with that said, that's how you're going to account for the horizontal asymptote, because the ratio of the lead coefficients, if the degree is the same, will be 3 over 1. Okay, I've used all the information except for this -10.8. So what I'm going to do right now is transition into Desmos. I've plugged in the equation we've written so far so you can see what's going on. Okay, so this is my equation. My rational function looks pretty rational. My whole was at 4. So I want to see what happens at 4. And we're just going to do this. So close to 4. Can I get it? Yeah. So it says 4 undefined, and the reason it's undefined is because it's a whole. But if you actually notice what that point is, and I'm just going to do this so you can see it. So let's see, my whole was at 4, comma, where's my comma? Negative 10.8. Okay, so here's the point, and the point at 4 actually is at negative 10.8, as you can see here. Again, it's not undefined right now because this has filled it in, but I just wanted to show you that the y value, even though I didn't use it to write my equation, is at negative 10.8. Okay, and the reason it is where you want it to be is because everything else in the equation has influenced the y value to be there. So you actually don't need to use the y value in this case. It's going to work out the way you want it to. Now in polynomials and quadratics, I know typically like if you have a quadratic, you got to solve for that like a value, right? And we didn't do that here. Good news is the reason we didn't need to solve for the a value is because you were given the horizontal asymptote, which actually told you what the a value was. It's the ratio of the lead coefficients. So if you weren't given the horizontal asymptote, you might need to solve for a. Okay, but since I was given the horizontal asymptote, I know what that multiplying factor is without solving by plugging in like the y-intercept. So in a different problem, you might get no horizontal asymptote, you might get the y-intercept, and then you would want to put an a here and solve for it. So just keep that in mind for future problems. It's not that it doesn't happen in this kind of function, it's just that it was already taken care of. Okay, what I'd like you to do right now is you have this problem that's a little bit different. It's writing an equation from a graph. Okay, but all the same things apply, so I'd like you to try it on your own, and I'm going to pause, and you're going to pause, and I will come back with the answer for you to check. No cheating, won't help you learn. Okay, if done correctly, you should get this critical information from the graph, so I just pulled that and wrote it down. Note that this is a hole. I know it's like filled in with gray, but it's supposed to be empty. And then f of x should look like this. And I should have mentioned before, you can leave it in factored form. Don't waste your time and multiply it out. Okay, so key things to note is that if there is a horizontal asymptote and not a slant asymptote, that means the degree in the numerator and the degree in the denominator should be the same. So like if you were to distribute this all out, the lead coefficient would be 3x squared, and here it would be 1x squared. So since the degrees are the same, it's going to have a horizontal asymptote. If you got that there were like x cubed up here and x squared, then there'd be a slant asymptote, and that wouldn't match this graph. So if for some reason you don't have enough x's, that's a good way to like double check if you've done the problem correctly, or maybe you'll need to solve for one. So anyways, that is writing equations of rational functions. Essentially, if you understand how to graph, you're just going the opposite way and putting it back in the equation, and this shouldn't be too bad. If you have any questions, please bring them to class, and have a great night.